Oh, hello and welcome to today's lecture. And we'll start by this lecture is in continuation on the gas power cycles. So I will start by recapping on what we know so far on the power cycles. Okay, so we know that for generating energy, a large scale use of molecular or nuclear energy is based on the evolution of heat and the subsequent conversion of that part of heat into useful work. Such systems are known as heat engines. Okay, and part of the heat received by a heat engine is converted into work while the rest is rejected to a sink. Okay, we've seen this already in previous lecture on the steam power cycle, where the source of heat could be any fuel like the nuclear or coal in terms of power plant. Also, we have other hydrocarbons like diesel or even natural gas, which are used to generate the heat source. Okay, and that is done in a boiler. So the high temperature source in this case for the power plant will be a boiler. Okay, and the total heat is added to what? The working fluid. The working fluid here is water most of the time, and the water absorbs this heat and changes phase from liquid to gaseous phase. And that change of phase from liquid to saturated vapor or superheated vapor, depending on what cycle you are looking at for your power plant operation, then some of the energy of the phase change into gas will be used to do a useful work, and that useful work is what happens in the turbine. This is where the gas will move the shaft in the turbine, and that shaft will be used to connect to generators that will generate electricity. Now, there is heat loss. Okay, there is heat loss in the process or reduction in temperature in the process, and that particular heat loss goes to a low temperature sink, and this is where the low quality steam leaves the turbine, goes to a condenser, and that particular heat will be removed completely in the condenser, and the working fluid is pumped back to the boiler, and the process repeats itself. So this is just to establish that the total heat supplied from the high temperature will be used to do some work, and some of that heat, the remainder from the difference of the work done, will still be lost to a low temperature sink to complete the cycle. Okay, so the heat engines are devices or systems that convert heat to work. They receive heat from high temperature, it could be solar, nuclear furnace, and used to move a rotating shaft like in the turbine. And the rejected heat will be dumped back into the atmosphere from if you have seen any videos or in real life, if you've seen some of the power plants, you will see cooling towers. So the cooling towers are more or less the condensers. So some of the heat will be lost to the atmosphere, and in some stages they run off the water to rivers and collect fresh cool water to continue the process. Okay, so and this operates in a cycle. So with this we can establish what the thermal efficiency will be. So the thermal efficiency will be the network, okay, the network output. So the difference between the work done in the turbine minus the work done by the pump to get the working fluid back to the boiler or the furnace or whatever, then will be the network divided by the total heat added in the boiler. Okay, and that will give you the network. That will give you the thermal efficiency for these heat engines. Now, we've established that the network could be the heat in minus the heat out, or the other way, the work done by the or it could be calculated as the work done by the turbine minus the work done by the pump to give you the network. So, and with this, we can also rewrite this equation, replacing network with Q in minus Q out. And if we do that in this equation, then we will have Q in divided by Q in minus Q out divided by Q in. And Q in divided by Q in becomes 1. And that's what we have here. And we'll be left with 1 minus Q out divided by Q in. So this is another way to calculate the thermal efficiency if you do not have the information about the network done by the system. Okay. So the Kelvin-Planck statement of second law of thermodynamics, which says that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a amount of work. So with this, we have established that the thermal efficiency of heat engines can never be 100%. Okay, they cannot achieve 100%. So this limitation applies to both fully reversible and idealized and actual heat engines. So the impossibility of having 100% efficiency in the heat engine is not due to friction or other dissipative effect. For a power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So there are other factors that that affect the possibility of achieving 100% efficiency. So these could be narrowed down to internal and external reversibilities. So a process is internally reversible if no irreversibilities occur inside the system boundary during the process. So during an internally reversible process, a system proceeds through a series of equilibrium states. And when the process is reversed, the system passes through exactly the same equilibrium state while returning to its initial state. So the quasi-equilibrium process, which is a slow process, is an example of an internally reversible process. So a process is externally reversible if no irreversibilities occur outside the system boundaries during this process. So a process is totally reversible or simply reversible if it involves no irreversibilities within the system or its surrounding. So if it is both internally and externally reversible. So for a system that is closed, okay, in like this, there wouldn't be any, there will be no irreversibilities if it does not uh, uh, interact, okay, with the outside, surrounding. Now, for you to generate irreversibilities here, then then you need to make sure that the system is the system has a kind of a finite difference in terms of the temperature or in terms of other physical property between the content of the system and the content of and the surrounding. Okay, so a totally reversible process involves no heat transfer from a finite temperature difference. So like I said, there has to be a finite difference in the properties of the system to the surroundings in order to achieve irreversibilities here. Okay, so if there is a very small difference, let's say in temperature between the system here and the surrounding, then there will be a quasi-equilibrium that will be achieved, which is a very slow process, meaning that the temperature change between these could alternate in equilibrium process, okay? So in a quasi-equilibrium process. So for us to make sure that there is no irreversibility, then there has to be a finite temperature change or finite temperature difference or even pressure difference within the system and the surrounding. Okay, so the Carnot cycle is the most efficient cycle that can be executed between a heat source at temperature TH and a high temperature and also a sink at temperature, a low temperature. So any heat engine has a thermal efficiency with respect to the heat loss and the heat added to the system, but the Carnot heat engine has a thermal efficiency with respect to the temperature at low reservoir and temperature at high reservoir. Okay. So the Carnot cycle is totally reversible. It is made up of internally reversible processes and is also externally reversible. So the Carnot cycle can be executed in a closed system like a piston cylinder device, okay, as you can see here, a compression process in a piston, or it's a steady flow system, okay, utilizing two turbines and two compressors. So we have the fluid going from stage 1 here into the turbine, does work in the turbine and leaves at stage 2 here, goes into the second turbine and does a network, useful work here. Now the remainder of the fluid will pass through the system again back to the first isothermal compression, constant temperature compression, where the heat is removed and goes into the isentropic compressor again where it returns to the first turbine. And it's a flow system, steady flow system that stays in a cycle. Okay, so this could be either the working fluid could either be gas or vapor. So we can represent this on the Carnot cycle on a PV diagram or a TS diagram. So representing it on a PV diagram, we have a process like this. So there are centropic processes which occur between stages 1 to 4 and 2 to 3. This is where uh, the uh, the entropy remains equal for the two stages. In this case, entropy at stage 1 and 4 are the same. Entropy at stage 2 and 3 is the same. Now, in between these two, there is a system in between, and this system is where we have the heat added between stages 1 to 2 and the heat loss between stages 3 and 4. Okay. So if we present it on a TS diagram, temperature entropy diagram, then we can see the stages represented here as well. So as we can see clearly with this TS diagram, that you see the entropy reading here is the same for 4 and 1. Entropy reading here is the same for 3 and 2. Now the temperature reading for stages 1 and 2 are the same because it's an isothermal process, and the temperature reading for the stages 4 and 3 is the same because it's at the low temperature reservoir. Okay, so for a closed system of compression, uh, we can identify that adding a heat source to the gas here will increase the pressure within the system and therefore increasing the volume of the gas here, moving the piston. Okay, if we go to this stage and with insulation, the process will continue until it gets to stage 3. Now, if you leave the system for a little while, the piston will return to stage 1. Okay, the piston will return uh, from this stage. We go over to this stage where the heat within the gas is removed. As the heat within the gas is removed, the temperature and pressure within the gas will drop as well. The temperature and the pressure will drop, and as temperature and pressure drop, the activities of the gas minimizes and it falls back the volume. This affects the volume of the gas, and the system goes back to its original state. Okay, and this system is reversible. So on a steady flow system, like we've explained already, from the state 1, we have the initial turbine, and in this turbine, there is a big issue here with the Carnot cycle. Some of these are not achievable. Okay, adding heat in a turbine. Okay, so uh, from stage 1, you see the heat is added to the fluid, the working fluid is expanded, and it goes to the second turbine doing the work is required, the useful work. Then it returns back to stage 3 where it is compressed and the heat removed from it, and it goes back to the smaller compressor here to get it to the pressure of the turbine, and the process repeats itself. Okay, so for given source and sink temperatures, heat engines that operate on Carnot cycle, which is totally reversible cycle, have the highest thermal efficiency of all heat engines operating between the same temperature level. So nobody can develop a cycle more efficient than the Carnot cycle. But unfortunately, we cannot achieve Carnot cycle in reality. Okay, there are so many issues of Carnot cycle. The thing is that the reversible isothermal heat transfer is very difficult to achieve in reality because it will require very large heat exchangers, okay, and it will take a very long time for that is a power cycle in a typical engine is completed in fraction of seconds. So uh, to achieve a reversible isothermal heat transfer will take a very long time, and we don't need that time. We want the heat transfer to happen in seconds. Okay, so it is not practical to build a heat engine that would operate on a cycle that completely approximates Carnot cycle. So the analysis of more complex processes can be reduced to manageable level by using some idealizations. So when the actual cycle is stripped to all the internal irreversibility and complexities, we have a cycle that resembles the actual cycle closely, but it is made up totally of internally reversible process. And this is what we call the ideal cycle, as we can see here. So the actual cycle is represented in the dotted pink lines, while the ideal cycle could be represented with a solid black line. Okay, so we use the ideal from the Carnot cycle to kind of like approximate what the ideal cycle could be. Okay, so modeling idealized systems provides great insight and simplicity at the expense of some loss in accuracy. So even though obviously it's an ideal cycle, so it's going to be a little bit different from the actual cycle, the real life scenario. Okay. So what is the difference between the reversible cycle and an ideal cycle? So reversible cycle, as example, cannot totally reversible both internally and externally, and they have the highest thermal efficiency of all heat engines operating between the same temperature limits. That is the source of the heat and also the sink. They are unsuitable as a realistic model. Most cycles encountered in practice differ significantly from the reversible cycle in terms of hardware. So for ideal cycles, they resemble the actual cycle closely but are made up of internally reversible process. They are not typically externally reversible, and they have a thermal efficiency less than that of a total reversible cycle operating between the same temperature limit. So they have a thermal efficiency considerably higher than that of an actual cycle due to the idealization. So this is the key major differences between the ideal cycles and the Carnot cycle. Okay. So the main idealizations and simplifications in the analysis of ideal power cycles are that the cycle does not involve friction. Okay, these are irreversibilities. The things that we friction is one of the things that brings about irreversibilities in the system. If we want to idealize the system, we can assume that the cycle do not have friction. Okay, so we assume that there is no pressure drop experienced by the working fluid as it flows through the pipes and the different components of power cycle, which we know that this statement is not it's not a reality, it's not what is experienced in reality. Okay, no matter how smooth the pipe is, no matter how good and machined the pipe is, that it's bound to be pressure drop within the flow in any pipe system. Okay, so all expansion and compression processes take place in a quasi-equilibrium manner. Now remember what we said. A quasi-equilibrium process is a very slow process. Now in reality, you want things to happen in a fraction of a second so that you can take the full benefit of these equipment. So there is no heat loss from the system. All pipes and other components of the system are well insulated, and heat transfer to the surrounding is negligible. We all know that no matter the level of insulation you put to equipment that involves the heat, the change in heat with the surrounding, there is bound to be some level of heat transfer between the system and the surroundings. So by making these assumptions, we have actually achieved an ideal cycle. Okay. So with this established, we can go further to introduce the gas power cycles. So in the gas power cycles, the working fluid remains a gas throughout the entire cycle. So in this case, if we compare the spark ignition we use for gasoline engine or the diesel engine that uses auto ignition for the process, so we can see that for a gasoline engine, the gas here is usually a mixture of air and fuel. So the fuel injector will inject the fuel, and there is an air intake which will come into the chamber here. Okay, and what happens is this is a vapor, in this case air fuel mixture, which is referred to as a vapor, as fuel or gasoline in this case is volatile, and if it's injected in small particles, it will form a mist, which could be referred to as a kind sort of gas. Now, when the process of ignition due to the spark plug igniting this at a certain pressure, then what happens? A mini explosion occurs, and that mini explosion uh, we is a combustion process, and we know the product of combustion, which is carbon dioxide and water, and with other materials as a result of the makeup of the fuel. Okay, other materials that also, but the predominant one for combustion is mainly carbon dioxide and water, and that is also a gas. Okay, the exhaust gas as a result of that mini explosion. So this means that the working fluid remains gas throughout the process, the beginning and the end of the process. Okay. Similarly, the same situation for the diesel. But the diesel obviously do not have a spark plug. The fuel are injected, and the air is allowed to come into the system, to mix with the fuel spray, and this is compressed to a pressure that we get the fuel, in this case diesel, to its auto ignition point. And when it gets to its auto ignition point, it ignites and explodes. Mini explosion occurs, and that mini explosion, as we said, we is a combustion process, and the byproduct of combustion is what? Carbon dioxide, water, plus other components of a suit, and all of that are just in the gas phase as well. So the working fluid remains gas throughout the process. Unlike the steam power plant, we know that at some stage the working fluid is going to be condensed completely into a liquid water or saturated liquid before it is now converted to saturated vapor again or superheated vapor. So, but in this case, the cycle, the working fluid remains gas throughout. Okay. So in all these engines, energy is provided by burning a fuel within a system's boundary. They are internally combustion engines. So even though internal combustion engines operate on a mechanical cycle, the piston returns to its starting position at the end of each revolution. So the piston will always return to its starting position at the end of each revolution. The working fluid does not undergo a complete thermodynamic cycle. Okay. So it is thrown out of the engine at some point in the cycle. This is the exhaust gas from the exhaust valve. So instead of returning to its initial state. So because of this, we can say that it's an open cycle. Okay. So, and that is a characteristic of combustion engine. Like I explained initially, the intake valve is where the fuel air mixture for a gasoline engine, the fuel gasoline mixture, fuel and air mixture is allowed into here. Now, what happens is that the piston obviously compresses that mixture, and the spark plug should be somewhere here. And as it compresses that mixture, the spark plug ignites the fuel, and as it ignites the fuel, the mini explosion will expand this region, pushing the piston away, and the piston gets to the BDC, okay, the bottom dead center, and what happens? The piston returns, and as the piston returns, what we have here now will be the remnant of or the byproduct of combustion due to that spark ignition explosion here, and that combustion uh, product will exit here. And as the piston is returning, the exhaust valve opens to allow the exhaust, the byproduct of combustion to leave, and the piston will always terminate its stroke at the TDC, the top dead center. Okay, there is a reason for this, to minimize faults in the engine. Okay. So the combustion process is an internal combustion. In an internal combustion engine means that the combustion of the working fluid changes from air and fuel to combustion product during the course of the cycle. So, however, to simplify analysis, the working fluid is considered to be air. So, is this a reasonable assumption? Because air is predominantly nitrogen that undergoes hardly any chemical reaction, as nitrogen is always inert in air. Okay, but if you check the composition of air, you will know that nitrogen, if you do it by mole or by mass, it will fall within 79% or 71% of the, it will make up 79% or 71% of air, depending on whether you are checking the mole or the mass fraction. Okay, so meaning that you have a little amount of oxygen ranging from 21% to 23%, And there are other components of air as well. There are other elements that you can find in air. Okay, but being that nitrogen is predominant in air, in the air mixture, then but the fact that it's inert uh, makes it, but the oxygen is not. The oxygen contained in air is not inert. It's highly reactive. So with that, we refer to uh, we can reasonable assume, okay, air as a very good candidate for as a working fluid in a gas power cycle. Okay, but in actual gas power cycles, they are rather complex. So to reduce the analysis to a manageable level, we use the air standard assumptions. So the working fluid is air and continuously circulates in a closed loop and always behaves as an ideal gas. Now, these are all assumptions to qualify an ideal scenario or ideal conditions to help us to understand how gas power cycles happen. Okay. So all the processes that make up the cycle are internally reversible. The combustion process is replaced by a heat addition process from an external source, and the exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. Now, obviously, we've already established with a couple of examples of internal combustion engine, okay, that this is not true. But with this assumption, we can approximate and make some clear calculations to see where else we can apply this kind of understanding and knowledge. Okay, so for a cold air standard assumption, when the working fluid is considered to be air with constant specific heat at room temperature 25 degrees Celsius. But for an air standard cycle, a cycle for which air standard assumptions are applicable. So despite its simplicity and reciprocating internal combustion engine, uh, is one of the rare inventions that have proved to be very versatile and to have a wide range of applications. So we use this internal combustion engine obviously in cars, trucks, light aircrafts. We have ships and electrical power generators. Okay, we use some of these to we use these particular internal combustion engines to achieve most of these feet. Okay, so like we said, the stroke is characterized by the top dead center and the bottom dead center, and this is the maximum distance that the piston has to travel in between each of the cycles. Okay, and this is here because to control the behavior of the engines, and to keep it to a certain operating level, to monitor the efficiency and also the safety for safety reasons. Okay, so the ratio of the maximum volume formed in the cylinder to the minimum clearance volume is called the compression ratio of the engine. So the Vmax, which is the volume when the piston is at the bottom dead center, and the Vmin, which is the volume of the space, okay, when the piston is at the top dead center. So with this calculation, with these volumes, we can calculate the ratio. Okay, we can calculate this ratio, the ratio of compression. So we know that the compression ratio is a volume ratio and should not be confused to the pressure ratio. Okay. So the reciprocating engines are classified as spark ignition or SI engines, and the compression ignition are referred to as CI, depending on how the combustion process in the cylinder is initiated. So the spark ignition, which is SI engines, the combustion in the engine uh, the combustion in the engine happens when the air fuel mixture is ignited by a spark plug. Okay, and that's when we know it's a spark ignition process. And the ideal cycle for spark ignition reciprocating engine is called the Otto cycle. And I think some of you have come across this, even the experiments you've done so far. So this is referred to as the Otto cycle. Why the compression engine? like we already established for diesel, is a air fuel mixture. Here, the air fuel mixture is self-ignited as the result of the mixture being compressed to a point that the compression, obviously the pressure, will affect the fluid and it gets to its temperature, the self-ignition temperature. So every compound, especially hydrocarbons that are used mainly as fuel, or volatile liquids or volatile hydrocarbons that could be used as fuels, they all have their autoignition temperature or ignition properties. So, in this case, compression engine, this is achieved by compressing the fuel air mixture when it until it gets above its autoignition temperature, and by achieving that, the fuel itself ignites itself because it has reached that, it has surpassed the autoignition temperature. Okay, and this is mainly used in a reciprocating engine for diesel cycle. So, what are the major differences between the gas power cycle and the steam power cycles? So, the steam power cycles, the steam is an inert medium to which heat is transferred from a burning fuel or from a nuclear reactor. Then the large heat transfer surface are needed for the absorption of heat by the steam at a high temperature in a boiler, and for the rejection of heat from the steam at a relatively low temperature in the condenser. And because of this, there is a metallurgical limit, which is a disadvantage to the application of steam power cycles, because the walls of these heat exchangers can only handle, they have a limit of temperature that they can handle. Okay, and when you have temperatures exceeding those limits, then there is bound to be failure within the system. So the steam engines are limited to that extent. So in an internal combustion engine, on the other hand, a fuel is burned within the engine itself, and the combustion product serves as a working medium, acting, for example, on the piston in the cylinder. So meaning that as the combustion occurs, the actual combustion product, which is a gas, which is a mixture of soot, carbon dioxide, and water, will help to push the piston out, including the pressure as a result of the mini explosion. We have to push the piston, and as the piston returns to to the top dead center, it pushes this gas away. So the combustion byproduct also serves as a working medium. Now, the high temperatures are internal within the system and do not involve heat transfer. So the high temperature only occurs when the gas is ignited, when the mixture of air and fuel is ignited, okay, or when they auto ignite. Yeah. So that's when the high temperature exists, and it's all internal. There is no source of heat source from outside. So the burning of the fuel within the internal combustion engine does not complicate thermodynamic. This does complicate the thermodynamic analysis. Okay, so if you burn the fuel in the internal combustion engine, then the thermodynamic analysis is affected. So for both fuel and air flow, they flow steadily into an internal combustion engine, and the combustion products flow steadily out of it, and there is no working medium that undergoes a cyclic process as does the steam in a steam power plant. So in a steam power plant, the cyclic operation, the cyclic operation of the working fluid is an advantage over that of a gas power cycle. Okay, so we'll be going into more details on the Otto cycle. Cycle spark ignition engines for fuel gasoline engines. Okay, so we've already seen this for a four-stroke cylinder engine. We've already had a kind of explanation on this on the first lecture and or the second lecture. I can't remember, but we've already come across this. So, and going straight, we know that the process could be represented on a PV diagram. Okay, so on a PV diagram, at the initial state here, the pressure of the fuel air mixture is at the atmospheric pressure. Now, when the intake opens at stage 1, at the from this stage, okay, the at the top dead center, this is the as the fuel enters, it expands the content, the mixture of fuel and air expands the volume, okay, of the piston, and as the piston arrives at the bottom dead center, it comes back up. As it returns back up, it compresses that mixture of fuel and air from stage 2. And as you can see, the compression at stage 2 increases the pressure up to stage 3. And when the pressure gets to stage 3, the spark ignition ignites the fuel air mixture, and the fuel air mixture explodes with a very sharp increase in pressure due to the combustion, the explosion, the mini explosion. It gets to stage 4, and that mini explosion expands. Okay, that mini explosion, as it occurs, it will expand the piston again, pushing the piston away, and that expansion process uh, occurs from stage 4 to 5. And from stage 4 to 5, the piston returns to push out the exhaust gas from stage 6 to 1. Okay, so this process has been represented on a PV diagram for the four stroke cycle in an auto engine. Okay, so like we've already established, the from stage 1 to 2, this is the intake stroke, okay, which is essentially happen at constant pressure at the ATM, atmospheric pressure. Then during this, the piston goes outwardly to draw in the fuel and the air mixture, like we expect. Okay, it goes outwardly. So as the from the stage 2 to 4, obviously we have the compression of the fuel air mixture and the spark ignition by the spark plug, and followed by the combustion. So the combustion happens between stages 4 to 6. Okay, and as the combustion happens, there is an expansion. Okay, an expansion that occurs due to the movement, the force or the pressure exerted due to that mini explosion. It pushes the piston downward. Okay, so that's the power expansion stroke. Okay, so as the power expansion stroke concludes, then there is a return of the piston again, and as the return of the piston occur, as the piston returns back to the top dead center, it pushes off the exhaust gas. Okay, and that's what happens between stages 6 to 1. So the Otto cycle can be idealized as two constant pressure processes, two constant volume processes, and two adiabatic processes. And how do we achieve this? So we have the constant pressure process that occurs between 1 to 2 and 6 to 1. Then we have the isentropic process. No, we have the isobaric process that will happen. Okay, the isobaric process that will happen between stages 2 to 3, and there is the isochoric process, which is the constant volume process that will happen between stages 3 to 4. Then similarly, we will have the adiabatic and isentropic process from 4 to 5, and a constant volume or isochoric process that will happen between these two here. Okay, so and this is how we can achieve an ideal Otto cycle. So if we are to use an Air-Standard Otto cycle, then we can represent it on this. So we have the two constant volumes at this stage here, so which is stages 2 to 3 and 1 to 4. And we have our two isentropic reversible adiabatic process between 3 to 4 and 1 to 2. Okay, so if we are to rewrite it for the piston and air, like we've established on the previous slides, then the process will look like this. To move from stage 1 to 2, this will be an isentropic process, which will involve the compression of the gas, okay, as the piston moves up. Then the heat is added at the gas, and as the gas gains heat, it becomes more energetic, and it pushes the piston away. And this is although the volume remains constant, but the pressure increases as due to the addition of heat to the air. Okay, and when that happens, the obviously the piston moves to stage 4. And at stage 4, if the heat that was added to the air is removed, then the gas will lose temperature, and will become less energetic, and the piston will return back to the state. Okay, and that is represented on this PV diagram. So the air is compressed vertically and reversibly. Sufficient heat is absorbed by the air at constant volume to raise the temperature and the pressure to the values resulting from combustion in an actual Otto engine. So the air is expanded vertically and reversibly, and the air is cooled at a constant volume to its initial state. So we can redraw that same expression. In this case, it's a PV diagram. We can redraw it as a TS, temperature entropy diagram, and we will still have similar. We can now account for the relation of the temperature and the entropy. So which means that for stage 1 to 2, which is asentropic, we can clearly see that it has stages 1 to 2 have the same entropy. Okay, and stages 2 to 3, because there is heat addition, then there is increase in temperature between stages 2 and 3. Okay, and at this stage is isentropic, which is a constant entropy. Okay, and from stage 4 to 1, to return to its initial stage, there is a loss of heat, which also shows us the change of temperature from this point to that point. Okay, so the thermal efficiency of Air-Standard cycle or Air-Standard Otto cycle is shown as the thermal efficiency, which is equal to the net work divided by the total heat added. And the net work in this case is the heat in minus the heat out divided by the heat in. And if we divide heat in by heat in minus heat out by heat in, then this side will become 1, and we will be left with 1 minus heat out minus heat in. And that's another way to rewrite this equation. Okay, so as for the steam power cycles and the refrigeration cycles, we can apply the first law of thermodynamics to each process in the cycle. But in the Otto cycle, it can be considered as a non-flow system. So therefore, all the flow components of the the general thermodynamic law equation, we tend to ignore them. So the kinetic energy, the potential energy, and the enthalpy will be ignored. So in this case, because it's a non-flow system, then the difference in the heat added and the work done is now equal to the change in internal energy. Okay, and with this established, then we can say that between the stages 2 to 3, okay, the heat added to the system, we can say that between the stages 2 to 3, the heat added to the system, okay, at constant volume will be given as the change in heat between 2 to 3. So this is also equal to the change in the internal energy between stage 2 and 3. If we know the temperature at stage 2 and 3, and we know the specific heat capacity at specific volume, which is given here, then we can also use that to calculate. But if not, we can use the temperatures to read out the properties of air, which is the internal energy of air at these temperatures, to use that to subtract to get the total heat supplied at this stage. Okay. So for the air, when the air is cooled at constant temperature, at constant volume, between stages 1 and 4, so the total heat lost in the system or the total heat removed from the system will be represented as the change in internal energy at 4 minus the change in internal energy at 1, state 1. Then, like we know, if we know the temperatures at 4 and 1, and we know the specific heat capacity at constant volume, then we can use that to calculate. So the specific heat capacity is given here at constant volume, but you can also get that as an average of these two temperatures. You can look up the figure on property tables, okay? Property tables for air, okay? So the thermal efficiency of air could be written, as we've already established, as 1 minus Q out over Q in, or net work divided by Q in. So if we replace Q out and Q in, like we've established here, so Q out, which is CV T3 minus T in, Q in, which is CV C subscript V times T3 minus T2, and Q out, which is C subscript V times T4 minus T1. If we replace it in this equation here, then CV cancels out and we are left with T4 minus T1 divided by 1 minus T4 minus T1 divided by T3 minus T2. And we can use this to calculate the thermal efficiency of Air-Standard Otto cycle. Okay, so coming back to the compression ratio. So the compression ratio, which is a ratio of the volume at the beginning of the compression, okay, a compression stroke, which is the volume at the BDC to the volume of the at the end of the compression at the top dead center, okay, and it's given as the Vmax divided by Vmin, can also be written as VBDC divided by VTDC. So what effect will increasing the compression ratio have on the efficiency of the engine? So if we increase the compression ratio, then we increase the efficiency of the engine, and the increase this will also increase the work produced per unit quantity of fuel added to the system. So for this case, we can see that in this chart, if this is the efficiency on the y-axis plotted against the compression ratio, we can notice that for a typical gasoline engine, that the efficiency, okay, will fall between for a compression ratio of 7 to 10, the efficiency will fall between 55% to 63%. Okay, and as you can see, the increase in compression ratio increases the efficiency of the system. So the increase in the thermal efficiency with the compression ratio is not that as pronounced at higher compression ratios. Okay, as you can see, at higher compression ratios, we can see that the curve was initially going up and now it's trying to stabilize or at a efficiency less than 0.7%, at efficiency less than 70%. Okay, so when high compression ratios are used, the temperature of the air-fuel mixture rises above the auto-ignition temperature of the fuel during the combustion process, causing an early and rapid burn of the fuel at some point and points ahead of the flame front, followed by almost instantaneous inflammation of the end gas. So this premature ignition of the fuel, called auto-ignition, produces an audible noise which is called engine knock. And this is what we don't want in our engines. So because of this, we need to control the stroke size we have in the engine in order to control the compression ratio. Okay, so the auto ignition in a spark engine cannot be tolerated because it hurts performance and can cause damage to the engine. So the requirement that auto ignition not be allowed places an upper limit on the compression ratio that can be used in spark ignition internal combustion engine. Okay, and with this we can rewrite the auto thermal efficiency of the Otto cycle with the compression ratio, accounting for the gamma, okay, to solve for the thermal efficiency. So example, the first example for the Otto cycle. So we have air at 100 kilopascals and 20 degrees Celsius, and it's compressed reversibly and adiabatically. The air is then heated at constant volume at 1500 degrees Celsius. The air then expands reversibly and adiabatically back to the original volume and is cooled at constant volume back to the original temperature and pressure. The volume compression ratio is given as 8. So calculate the thermal efficiency, calculate the heat input per kilogram of air, calculate the net work output per kilogram of air, and the maximum cycle pressure. Okay. So going back to the PV diagram, we can plot out the whole cycle. Okay. We know that the heat added is between stages 2 and 3. We know that the heat removed is between stages 4 and 1. And we know that the maximum pressure in the system is at stage 3. As we can see from the plot, that at stage 3, this is where the cycle operates at higher pressure. Okay, so the initial state, we know that P1 from the question, it says the air at 100 kilopascals and 20 degrees Celsius. So at P1, we have the temperature of air at 20 degrees Celsius. We convert that to Kelvin. We have the pressure at 100 kilopascals. Now we have the for process 1 to 2, from 1 to 2, we are told that the ratio, the volume compression ratio is 8. So with this, the volume compression ratio here, which is V1 over V2, is equal to 8. Then at stage 2 to 3 occurred at a constant volume, and temperature at 3, this occurred at a constant volume. Okay, as we can see, the volume here, heat is added at constant volume. So at stage 3, we know that the temperature, so the air is heated constantly at constant volume to this temperature. So the air was heated from 20 degrees Celsius to 1500 degrees Celsius up to T3, and we can convert that to Kelvin as well. Now stage 3 to 4, which is another isentropic process, and it says the reversible expanded reversibly and adiabatically back to its original volume. So meaning that the compression ratio here is the same as that compression ratio here. So which is V4 over V3. The volume at stage 4 divided by the volume at V3 at stage 3 is equal to 8 as well. Now, what is the constant volume heat rejection at stage 4 and 1? So the heat rejection at stage 4 and 1, as we know, we can calculate that. So the P1 V1, using that expression for the pressure and volume and the gamma, and combining the effect of temperature using the full ideal gas law, okay, for an isentropic process, then we can rewrite this equation, which is here. We can rewrite this equation with respect to pressure P2 over P1 to volume. And since we have established that, we go on this equation, we rewrite this equation with respect to P2 over P1. So if we do, we get this particular equation. So P2 over P1 is equal to V1 divided by V2 all raised to power gamma. And similarly, with this equation, P2 over P1 is equal to T2 V1 divided by T1 V2. And since pressure is equal to this and also equal to this, then we can bring it together. So if P2 over P1 is equal to this and also equal to this, then that means V1 over V2 or raised to power gamma could also be equal to all of this. So that's what we've done here. And since we've done this here, then we can write the equation to with respect of the temperatures. Okay, so if we use this equation now, so here we have T2 over T1, and if we use this divide both sides. If we divide both sides by V1 over V2, and dividing this obviously with the power of gamma here, so it would be V this V1 over V2 minus with gamma minus 1. So this is just specifically laws of indices. Okay, if you can recall, you can attempt to do that. Then if we now arrive at the final equation, so the final equation will look something like this. Okay, and if we already achieve this, then we can calculate T2, since we know T1 as 20 degrees Celsius, and we know V1 over V8, which is the ratio, which is 8, then we can plug in the values to calculate for T2. Then what about P2, the pressure at point 2? We can calculate that using this equation here. So we know the expression as the V1 over V2 ratio, which is compression ratio, as 8, and we know that gamma is 1.4 for air, and we know that P1 is 100 kilopascals, and we can use that to calculate the pressure at P2. So for the temperature, we know the temperature at T3, so we can use this expression to calculate for the pressure at P3. So since we have the temperature and the pressure at P2, then we can plug in the values to calculate the pressure at P3, and that gives us 4.8 megapascals, okay, or 48 bar, okay. So to calculate for the isentropic expansion at between stages 3 and 4, so we can use the same expression which we've already derived from the previous slides, but in this case accounting for the stages. Okay, so we do the same. We have P4 over P3 is equal to V3 over V4 raised power gamma, then therefore T4 over T3 is equal to V3 over V4 raised power gamma minus 1. And with that, we can calculate for P4, since we know the value for P3 and we know the volume at stage 3, which is the same as volume at stage 2 and the volume at stage 4. So we have the ratio, and the ratio is 8. We can plug it in this equation to find the final pressure. And we do the same thing here. We plug it in this equation to find the final temperature at T4. Okay. So since we've calculated these temperatures, then we can apply this formula to calculate the thermal efficiency. And we've already established what the thermal efficiency is equal to. Then we can expand this equation to account for the temperatures. We can as well do this simple, since we know the temperatures, we can calculate the heat out and the heat in and use this, or we can directly plug in the temperatures in this to calculate it. And when we do so, we find that the thermal efficiency for this Otto cycle is 0.565, which is 56.5%. Okay, so the heat input per kilogram will be the change in heat between the two stages 2 and 3. So if we know the T3 and we know T2 and we know the specific heat capacity with respect to the volume, then we can use that to calculate the total heat added to the system. And if we know, and with that, we can calculate the work output per kilogram. Okay, so the work output per kilogram is when we take the difference between the work, okay, the work in and the heat in and heat out. Then we use that to divide the total heat into the system, and it will give us the network. Since we know the efficiency as 56.5%, and we know the total heat added to the system, then we can rewrite this equation to calculate for the network done by the system, okay, per kilogram, obviously. And we know that the maximum pressure is the pressure at stage 3 here, okay, because this is the highest reading pressure for the cycle. So, and we've already calculated that here. So P3 is 48 bar. So, and that is so that will be it for this particular lecture. And in the next lecture, we'll go over and discuss and introduce the diesel cycle. Okay, see you guys on the next one.